Repeated measures ANOVA is for studies where the same participants are used in each part of the test. The cool thing about it is that because we're using the same people, we can divide out something called the person effect, or how much each person varies on his or her own. Our mean square within subjects shows us how much of the total error we're able to take out because we use the same people repeatedly. Because our sums of squares total is smaller, because we took out the person effect, our sums of squares error is smaller too. This makes our f bigger because we're using a smaller denominator when calculating the f. So sometimes, if you calculate an f for repeated measures ANOVA and it's significant, the same data using a two-way ANOVA will not be significant because it'll have a bigger denominator with more error. Psychologists have found that if people take the same test repeatedly, they tend to do better on subsequent trials. This is called the practice effect, and it isn't true for all tests. Some tests, like IQ and the SATs, we don't want there to be a practice effect. So suppose we give 8 subjects a standardized admissions exam every Saturday for 3 weeks, with no studying in between. Will they get better? Okay, so part A of 14.1 asks to write the statistical model for these data. So we're looking for a model that means that data point, that person at that level of treatment at that particular test. So xij is the person at that level of test, equals mu, which is the mean, plus pi, which is the person effect, plus tau, which is the treatment effect. So the fact that you've done test 1, test 2, test 3. Then we have the pi by tau interaction, meaning that each person might react to the treatment differently. So we don't expect necessarily everyone to react to the first, second, and third tests in the same way. All of their lines might not be parallel. And finally, we have error, which is the average amount we expect people to vary across the 3 tests in general. And that is our statistical model. Okay, so part B is asking us to run the repeated measures ANOVA. So recall we have 8 subjects whose scores we have for the first, second, and third exams. So the first thing we need to do is to calculate our sums of squares total. So we take each of the scores, the 550, 570, 580, 440, 440, 470, etc. Take it from the grand mean, 563.333. Square each one, sum each one up, and we get a sums of squares total of 194,933.33333. Okay, next we're calculating our sums of squares subjects. So we take our subject means, so that's the column furthest on the right, the mean for each subject across the 3 trials, and we subtract from each the grand mean of 563.333. We square them, sum them all up, and times by W, which could also be T. It's the number of treatments. So in this case, there's the first, second, third. So that's 3 treatments, so we times by 3. And we get a sum of squares subjects of 189,666.6666666666. Okay, so now we are going to calculate the sums of squares treatment, which in this case is our sums of squares time. And to do that, we take each of the test means, so that's the row at the very bottom, and subtract from it the grand mean, square them, sum them up, and this time we multiply by small n, so the number of subjects in each trial, which is 8. So we multiply that and we get a sums of squares treatment of 1,808.333333333. Okay, next we're doing our sums of squares error, which is the same as it is always. It's just the sums of squares total minus the sums of squares subjects minus the sums of squares treatment or time. So that works out to be 3,458.3333333. Last but not least, we have our sums of squares within subjects, which is nice and easy. It's just our sums of squares time plus our sums of squares error. And that works out to be 5,266.666667. Okay, so I have taken all of our scores and put them into an ANOVA summary table. And now we have to calculate our degrees of freedom. So for between subjects, it's just small n minus 1, so 8 minus 1 gives us 7. Within subjects, it's n times k minus 1, so 8 times 2 is 16. For time or treatment, it's k minus 1, so 3 minus 1 is 2. For error, it's n minus 1 times k minus 1, which gives us 7 times 2, which is 14. And for total, it's just big N minus 1, so that's 23. Next, we calculated our mean squares, which were the same as they always are. So our within subjects mean square is 329.17, and that is the amount of error that we were able to take out or extract from our f, the denominator in our f, because we used the same people. That's our person effect. Next, we get our mean square for time treatment is 904.17. Our mean square for error is 247.02. We use those to calculate our f for treatment, which works out to be 3.66. Now, is that significant? We look up our critical f using 2 and 14 degrees of freedom, which is 3.74. So our obtained f of 3.66 is closer to the mean than our f critical. It's not in the critical region. So we fail to reject the null and conclude that it is not a significant ANOVA. We can say that people did not perform significantly different or better each time they took the exam. There was not a practice effect for this exam. Okay, so question 14.2 is asking us to run a paired samples t-test between sessions 1 and 2 of exercise 14.1, ignoring session 3. So what I've done is make a table with the first and second exam scores for all 8 subjects in the first 2 columns. And then I made a column of the difference scores between the first and second tests. And I took the average, the mean for that, which was 11.25. The next column is taking the different scores and minusing from it the difference mean. And finally, the last column, I squared each of these. So now we have all the information we need to calculate our paired samples t-test or our matched t-test. So first we need to get our standard deviation. So we plug in our sum of all the squared differences from the mean of the differences over n minus 1, square root that, and we get 27.99. We put that over the square root of n, which is 8, and we get a standard error of the differences of 9.89. Plug that into our t equation, divide our mean by our standard error, and we get a t score of 1.136, which is not significant. Okay. Now we are running a repeated measures ANOVA on the same data that we just ran the paired samples t-test on. So we need to find our sums of squares total, our sums of squares between and within subjects, our sums of squares time, our sums of squares error, our degrees of freedom, our mean squares for time and error, and our f. So I'm not going to go over all of them, but here's all the equations for our sums of squares. for our degrees of freedom, and I've put them all in an ANOVA summary table here. We get our mean squares by dividing our sums of squares by its degrees of freedom, and then we get our F for treatment by dividing the mean square treatment by the mean square error. So we get an obtained F of 1.292. Compare it to our F critical with degrees of freedom 1 and 7. So that F critical is 5.59. And so our obtained F is not significant. There is no difference between the first and second exam. Furthermore, the obtained F value of 1.292 is equal to the square of the obtained T value, 1.136. So that was the homework for the repeated measures ANOVA, question 14.1 and 14.2. The answers for 14.6, the two-way mixed design ANOVA, will be in the next file in part 2. So stay tuned!